Thank you. Thank you very much. I have no idea what Jesus just said about me, so I hope it was nice. We'll see. It is such a pleasure to be here. It really is. Thank you very much for the invitation, for this opportunity to speak with you this afternoon. Jesus asked me to talk about what we've learnt around computing education over the last 3 years in England, because it's just over 3 years ago that we put computing as a new subject onto both the primary and secondary national curriculum. But the story really starts about 5 years ago when we decided we were going to get rid of the old subject ICT and create this new subject computing. I want to tell you something of that story. In fact, as far back as 2010, we decided that the English national curriculum, the national curriculum in my country, wasn't really what it should be. And so Tim Oates and others went and looked at what was happening in other jurisdictions, how other countries structured their curriculum, and saw if there were lessons that we could learn in England from how curriculum was developed elsewhere. And the point that Tim Oates makes here is that in high-performing jurisdictions, they have these 6 things all working together to ensure an effective curriculum. The content, yes, of course you need to get the content of curriculum right, but also the assessment mechanisms, the how it is taught, the pedagogy, training teachers, professional development and initial teacher training, the teaching materials, the resources we use, as well as this notion of incentives and drivers. And I'm going to use that as the structure for what we're going to talk about in the next 40 minutes or so, of looking at each of those in turn and seeing whether we have got as far as this idea of a coherent curriculum in England. We do this at the time back home of a period of small government, of my government stepping back from implementing change themselves. The phrase they use there, government should only do what only government can do. It's an era in which government is deliberately not dealing with much of what government might once have done within the past. So yes, we have put computing onto the curriculum, and central government had to do that. It had to say, this is what should be taught. But alongside that, we have a reluctance on the part of central government in England to actually deal with the implementation, to produce training programs, to produce teaching materials, to develop resources. And they've let that be something which we as a community of teachers have helped with and which industry has contributed to. So yes, the aim is a coherent curriculum, but the means of delivery, the means of achieving that is very much one of, let's see what a big society of industry and academia and teachers, as well as some local government and central government can do together. So let's start with the content question. As I say, 5 years ago, this October, sat in basement conference rooms in our Ministry of Education and in the Royal Academy of Engineering, trying to draft a curriculum for computing. The Secretary of State announced the following February that they had replaced the old ICT curriculum with a new computing curriculum with help from Google, from Facebook, and some of Britain's most brilliant computer scientists. I really do not think he was talking about me when he was talking about Britain's most brilliant computer scientists. And the Facebook thing there, I remember one meeting when there was one person from Facebook. I don't recall them actually contributing much. I think they just liked what we'd done. We did have a big part, a big tent. It was a diverse collection of organisations that were represented around the table. So yes, we had government. We had sector bodies like the Royal Academy of Engineering, British Computer Society. We had universities, both teacher training and computer science, and we had teachers around that table. And I think, if we are going to claim that what we've written is a success, it's because of that diverse group of stakeholders meeting together to develop a curriculum. We start the new curriculum with this level of ambition, that a high-quality computing education equips pupils to use computational thinking and creativity to understand and change the world. And, checking whether this has actually worked. Have we implemented this well? You just go up to the child and ask them, have you understood the world? Have you changed the world? And if they can say yes to both of those, then clearly we're doing a good job. The computational thinking is new. Creativity is so important. Primary and secondary education should be about creativity, but computational thinking sits alongside that. What should education do? It should equip young people to go out of school understanding the world in which they find themselves and being empowered to make a positive difference to that world. And computational thinking and creativity, I hope, try to do that. The new curriculum in England is not just a coding curriculum, it's not just a computer science curriculum. We call it computing, and we recognise that there are three quite definite elements to that: computer science, information technology, and digital literacy. I think it's helpful to think of those in terms of the foundations of the curriculum, its applications, and then some consideration of the implications for this. So the foundations, yes, the fundamental computer science. The applications, those good old-fashioned IT skills, being able to word process something, being able to make a presentation, being able to make a video, as well as some consideration of how to keep myself safe, how to act responsibly, and the implications of this for a broader society. You can think of this in terms of the question, how does Google work? So at the applications layer, the IT layer, how does Google work? Well, you type the words in and click the button. Okay, there is more to that. There's filtering results and advanced search. But at a computer science layer, the foundations, how does Google work is about making cached copies of web pages, following those links, using the PageRank algorithm to select and rank the results that are displayed. But how does Google work is also an implications question. And yes, it works by employing really smart, creative people. It also works by building up a very detailed profile of what it is that I'm interested in, what it is that I search for, so they can better target advertising that I'm more likely to click on. And we ought to have children thinking about all three elements of that in something which they use. So what did we put onto the curriculum? Well, we didn't put lots of coding for our under fives. You'll be, I hope, pleased to hear. What we have for the under five curriculum, we call it the early years foundation stage, is a recognition that children should be creating things and thinking critically about things. None of this needs a computer, but we want our youngest children, our 3- and 4-year-olds, to have their own ideas, to find ways of solving a problem for themselves, to find new ways of doing things. We want our youngest children to make links, to make predictions, to test their ideas. And we want our youngest children to be willing to check how well their activities are going, to change strategy as needed, to review how well what they're doing is working. This doesn't need a computer, but if this is going well with 3- and 4-year-olds, it lays a very firm foundation for, yes, the computational thinking and the creativity that will come after this. I've talked to Google engineers. What is it you're looking for when you recruit? And they say, well, pretty much those things. So, what we know about computational thinking starts in kindergarten. I'll give you a moment to copy down the details here. No, so this is the 5 to 16 curriculum. It fits onto 3 pages of A4. It is very, very terse language. This is what children should be taught. So yes, our 5 to 7-year-olds start with understanding what an algorithm is, a sequence of instructions, a set of rules, and know how that can be implemented as code, as a program, on a simple digital device. Doesn't have to be a computer. Our 7 to 11-year-olds, yes, understand about algorithms. They think through code logically. They should be able to read code as well as write code. And yes, they should be able to use things like sequence, selection, repetition, input, output, and variables in a simple block-based language such as Scratch. For our 11 to 14-year-olds, we want them, yes, to develop that using perhaps another block-based language like Snap, but also to start writing text-based programs, typically in Python these days, and to understand some of the classic algorithms like algorithms for search, algorithms for sort, algorithms for checking whether a number is prime or not. So understanding some of the classic algorithms from computer science is part and parcel of what happens there. For 14 to 16-year-olds, the status is a little bit weird in that we have computing on the curriculum for all 14 to 16-year-olds, but we recognise that many of them will choose not to take a qualification. So all we require is that they continue to develop these skills, continue to be able to apply these concepts. But we make the opportunity available to all that they can study for a qualification if they wish to do so. So thus we've developed new qualifications in computer science, which are academic, which are rigorous, which, yes, require programming projects, but also really do test whether a young person has that understanding of the principles of computer science as well as the ability to write code. And we have that at both GCSE 16-year-olds and A-level 18-year-olds. More of that later. So Tim Oates argues that as well as curriculum content, all of which is really very easy, we also need to develop an assessment methodology for this. And so in the national curriculum, we have this standard statement for every subject, for every key stage, that at the end of each key stage, at 7, 11, 14, 16, we should know whether the young people have understood, do they know, apply and understand the matters, skills, processes specified in the curriculum? So this is what we should teach. Have they learnt it? Is all that's required in terms of assessing the national curriculum. How you go about that is left to teachers. Remember, government has stepped back from implementation and left that to us. So one of the things which we did was to produce, again, 3 pages of A4 of the individual statements of what a child should know according to the national curriculum. We've put those into order, we've put those into 3 columns, so we have some way of assessing at a granular level whether a child has grasped a particular idea. You should be able to look at a Scratch project and see whether the person who's written that code understands the idea of repetition, understands selection, understands variables, and of course we have lovely Dr. Scratch which can help us make that sort of judgment. But looking at projects is only part of the process here. We can test some sort of skills by looking at the projects which a child does. But there's more to it than just their skills, more to it than just the projects that they make. And so for assessment generally, we've moved away from this fairly abstract notion of levels of attainment, sort of a 1 to 10 scale, as I think it is here, to something which is much, much more granular. And the recommendation from the assessment panel was that we should develop some questions, a national item bank of typically multiple choice questions that teachers could draw on to test whether the children in their class have understood an idea. Yes, look at their projects, but also ask them some questions. Maybe ask the questions before you start teaching it. If they already know the thing, you probably don't need to teach it. Ask them the questions during the lesson. Do you understand the idea I've just explained? And ask them the questions at the end of the unit. Have they understood the thing which they've spent the last 6 weeks working on, perhaps? So we've rolled up our sleeves and got on with this. We have a thing called Project Quantum, which is crowdsourcing this item bank of what we have now 5,743 multiple choice questions for assessing computing. All, I'm afraid, written in English. Sorry about that. Okay, they're free. Free in the sense of anybody can use them, free in the sense of there's no charge for this. It's meant for formative assessment. You can't use this for high-stakes summative assessment because we're letting young people themselves come and have a look at the questions beforehand. It's all done online. The machines mark these automatically. Our aim is for high-quality questions, and we're going to use some clever data science to work out which the highest quality questions are. And the idea is this is a resource to support teachers, not some sort of big stick formative, summative assessment tool. So one of the questions, one of my favorites on the right there, we have a little bit of Python code. You know, if you type in 1, it goes one way. If you type in 2, it goes the other. 44% of the young people who take this question give the wrong answer. They pick answer D for this question. Correct answer is, in fact, you choose 2, answer A there, because they've not spotted that Python assumes you're typing in a string of characters rather than assumes you're typing in a whole number. Sorry, a little bit of technical knowledge there. So come GCSE, our 16-plus qualification, we want them to do some project work, but it's a very constrained project at the moment. It is, here is a particular task. We want you to write a program that implements. So this cows and bulls game, it's like the mastermind game. It's a pattern matching thing. So a very, very clearly specified statement of the problem, and young people have 20 hours to produce their solution and test their solution and document their solution to that. There's a very constrained way of testing whether they can write code in response to a particular challenge. At A-level, our 18-plus qualification, much, much more ambitious. So we're introducing, by that point, other programming paradigms. Object-oriented programming comes in by that point. Functional programming comes in by that point, which used to be part of, first-year undergraduate computer science, if even then. And we have a much more open-ended project. So for our 18-plus qualification, what we call A-level, young people can make whatever they want. It has to be something ambitious if they're going to get the top grades at this, but it's a very open-ended project, and they will spend a number of hours working on that independently of their teacher to produce, a bit of software, a program that does something amazing, we hope, or at least something interesting. What about the questions of how do we teach this? This isn't like maths education or science education or first language education, where we've worked out for a long period how to teach this effectively. I'm not saying all teachers do teach these subjects effectively, but we've got a body of knowledge we can draw on about what is effective practice in these domains. The pedagogy question for us in computer science is much more open. We're still trying to figure this out. I think for teachers in England, we have this sort of two-stage model for programming. Writing a computer program is a two-step process. Firstly, how are you going to solve the problem? And then, and only then, write some code so that the machine will do that. We build that into the curriculum. And that, I think, is how many teachers in England are approaching programming education. Firstly, do the planning. Think of how you're going to solve this. Sometimes writing that as pseudocode, sometimes writing that as a flowchart, but very much emphasizing the importance of the planning phase, not just going straight to the coding phase. There are products around which focus just on one or the other. So we have, just teaching children about algorithms. What's your algorithm for making a jam sandwich, which you never write a program to do. We also have plenty of things around where it is, here are some instructions, follow all of these instructions, look, you have written a computer program, without developing that understanding of the algorithms, of how to solve the problem, when we think both go together. So I've mentioned two of these already. We have that sense of progression, which again is something Tim Oates argues curriculum should do. Our youngest children are not coding on screen typically. They're coding with one of these things. This is called a Bebot. Heaven knows why it's called a Bebot. There might be a clue there, I don't know. It's a tiny wee little robot that trundles around on a table. You can create a sequence of instructions. You press the buttons in order, it remembers the order you press the buttons in, click on the big green button marked go, and it trundles off and does this. It's not a universal Turing machine. It's very limited in what it can do, but it gives the child that understanding of how I'm going to solve the problem and then write code in one particular computer language, forward, turn right, forward, which they can then program into the device. For primary pupils, we're using Scratch very, very extensively. Yes, other languages are available, but I don't think any of them are as good as Scratch. And Scratch starts with this notion of the open-ended project, of make something that you're interested in. And a lot of teachers are allowing children to do that, but we're also scaffolding children's programming in Scratch. The advantage of using something like Scratch, the block-based language, is it separates out the need to master the syntax. Yes, they are writing code. Of course they're writing code, or at the very least making code. They're translating their idea of the algorithm into a program that the cat, whichever sprite they use, can follow. But there's no need to remember where to put the semicolon. There's no need to remember about the indents. All of that is managed automatically within the block-based language as you build it up. And then we want them at some point in secondary education, before the age of 14, to make the move into Python. And a lot of the work that's going on in secondary schools is thinking about how to support children as they make that transition. I don't think we've yet found the perfect solution. One of the approaches we're doing is looking at the same problem in both languages, solving the same particular challenge in both Scratch and Python. So they think perhaps in terms of Scratch and then translate it into the text-based language, allowing them to focus on one thing at a time. Firstly, how are you going to solve the problem? Then write that as code in a language which demands a certain amount of syntax. Typically, by the age of 18, they will be moving on from Python. I love Python, though, because of its wide applications in other domains. So we're seeing quite a lot of work with 16 to 18-year-olds around C#, around Java at that stage. And if you're doing that, the functional programming, we're seeing Haskell introduced at that point. But Python is very much the sort of favored programming language for secondary education. Mark Gosdale, writing back in 2011 about educators in higher education, remarked how many people who are teaching computer science at university take a very pragmatic approach. They think about what works for me, what works with my students. And I think this is what we see in the school sector as well. Teachers are not immediately interested in what is the research which underpins these particular pedagogic approaches. Teachers seem much more interested in, well, I've tried this seems to work with my classes. And we've done surveys, we've gone out and asked the question, or my colleagues Sue Sentence, Andrew Chismadier have done the survey and asked teachers, how are you teaching computer science? And we get answers such as using unplugged activities, stepping away from the computer, the jam sandwich type algorithm, as well as providing hands-on experience. Pair programming seems to be a very popular approach to programming in both secondary and primary education, of getting two children working together on the same screen, same keyboard, same mouse, so as to produce one program between them and talking to one another as they do that, and a number of the other approaches which they talk about as what works for them. Talking to teachers in England about how they're teaching computing, my own list of what we're learning, this sort of pragmatic approach to teaching computing, would be the 10 things on the screen there. This need to think through the program before you start coding, that yes, we don't have to use a computer to develop an understanding of computer science, although I'm coming round to the view that actually it really does help to use a computer for computing. I don't know. That reading code is really important before you start to write code, and actually having somebody else's program as a starting point for your own works as well. Also recognition that, as Papert said way back in the 70s and 80s, making things is so important. We want young people making things with code, not just reading code. Pair programming, as I've mentioned, fixing things when they go wrong and having a resilient approach when things do seem to go wrong with computers. Happens all the time to me. This is the more controversial one. I think it's better to master one or two languages rather than have a diverse experience across many. I want young people to get to the point where they can express their ideas fluently through the medium of code. So getting really good at Scratch, getting really good at Python before moving on to other languages. I have friends in England who I value very much, who take a very different position and say it's not about the language, it's about the concepts. My argument is you develop your understanding of the concepts through mastery of one or two languages first. We think context matters, so linking what they're doing in computer science, in computing classes, to what they're doing in other bits of the curriculum and what they're doing outside of school. Making music, making art, yes, making games, but not just making programs which test if something's a prime number or not. And finally, and I'll return to this before we stop, a recognition that this has to be an inclusive subject, that everybody should be able to take part in these lessons. So, just a couple of examples. Anybody familiar with this rubber duck debugging? Okay, so this is a thing which has really captured the imagination of teachers in England, certainly at this GCSE 16+ level. They're going to Amazon and buying tiny little rubber ducks which they stick on the computer monitor or on the laptop. What is the point of that? Well, the idea is that the young person, the student, tells the rubber duck what their program is supposed to do. They explain their code to the rubber duck. And somehow, by talking to the rubber duck about their code, they suddenly realize why it's not working. It's this idea of being able to explain what the program does. So all of a sudden, we've got lots and lots of teachers in England bringing rubber ducks into their class. This was posted on Facebook yesterday of the army of 30 rubber ducks who are going to go and help their 14, 15-year-olds with their programming projects. The relationship between coding and computational thinking is still not something which we're entirely clear about. We know computational thinking is what we're aiming for. It's how we justify teaching everybody how to program a computer. It's not just for those who are destined for careers in the software industry. So Code Club, which is an after-school primary programming club, 9 to 11-year-olds, they give an hour a week of their time to learn how to code computers. Yes, we're doing it in the curriculum, but it's lovely to be doing it after school as well. They did the randomized control trial study. So you get so many children turning up for Code Club one year. We put them into two groups. Half of them got the place in Code Club, the other half didn't. Gave everybody a test at the beginning of the year of how good is your coding, how good is your computational thinking. Let Code Club run for a year and test it again at the end. The children who went to Code Club got better at coding. That's good, isn't it? We'd expect that. The children who went to Code Club got better at computational thinking as well, but so did the other children. So Code Club on its own didn't seem to make any difference to how well these children progressed in terms of computational thinking. So my conclusion from that is that if you want them to get good at computational thinking, just teaching them to code isn't enough. You need to teach the computational thinking, teach strategies for planning, teach strategies for decomposing big problems into smaller parts. Don't simply expect a child to pick it up from writing code in Scratch or writing code in Python. To be fair, Code Clubs say, well, the questions you used weren't really tests of computational thinking, which is debatable. Okay, so on to home ground now. This is the thing which is my day job, training the next generation of outstanding teachers. And we start with the premise that if you want to improve the quality of teaching in an education system, by and large, that means improving the quality of teachers in that education system. And you have two ways to do that. You either recruit better people in or train those people who come into the profession better, or provide better professional development for all those who are already there. I don't think it's an either or, it's not an X or, it is an inclusive or. We want to do both of those things. Get teacher training right and get professional development right. So how do we get outstanding teaching of computing? The Mishra and Kohler work around the TPAC model says there's three elements to that. There's how you teach, there's your tech skills. Can you use the technology? Can you use Scratch? As well as your computer science subject knowledge. For what we did in England, at least initially, we kind of assumed teachers already know how to teach. We may have been wrong in this. We kind of assumed that teachers already know how to use the technologies which they need in their job. Again, we may have been wrong with this. But we knew that very, very few of our teachers, particularly in primary, particularly in lower secondary, had any background in computer science. So if we want outstanding teaching of computing, that's the low-hanging fruit. That's the thing that we had to get right, of giving them enough knowledge of computer science so that they could go in and pass that on to their pupils. I hope we've done that. So we drew up the subject knowledge entry requirements. We had this idea that there might even be primary specialists, specialist computer science teachers going into primary school. How much computer science should they know? What is the requirements for them? So they should be able to program before they start training to teach, because teacher training focuses on the pedagogy, focuses on the teaching skills, not on the subject knowledge. So we've used this, yes, as a framework for developing initial teacher training, but also as a framework for looking at how to structure professional development. When I survey my own students at Roehampton, first week of the course, we ask them to complete this self-audit. We don't do tests, they evaluate themselves across a range of different IT skills. And they say they're pretty good at email, they're pretty good at using social software. Is that true of Spanish students, that they're good at using social software? I'd expect so. Okay, but there's a range of stuff down the bottom there which they're not good at, according to them. They say that they're not good at programming. I have nearly 60% of my new students say they have never programmed before. I obviously have to address that in the course that I teach. We now also ask them about their knowledge of things. And that's okay across some of that. It's not nearly as good as their skills, but their knowledge of things that are now on the computing curriculum, like generalization, algorithms, logical reasoning, is so low. So my priority in initial teacher training, yes, teach them how to program, but also give them some understanding of logical reasoning, give them some understanding of abstraction. I do worry about the 50% of my students who say they have never used logical reasoning as to exactly how they chose to do the course which they've just enrolled for. It's just like random. You know, who knows? So that's the initial teacher training side, and I think we're getting there. CPD, the continuing professional development, again, government has largely stepped back from this, but we have the most brilliant subject association, the membership association, the community of practice for computing. We call it Computing at Schools, CAS. We have close on, just over 28,000 members now. These are teachers who are supporting one another in delivering this subject. They're academics such as myself, such as proper computer scientists. They're folks from industry. It's funded with support from Microsoft, with support from Google, with some support from the Department for Education. But it's free for teachers to join. And it's an international membership. If any of you would like to join, you would really be very, very welcome, of course. So Computing at Schools has really allowed teachers to support one another at a local as well as a national level. Computing at Schools runs this network of excellence in computer science education, because just working with 28,000 teachers is not an efficient way. So we've got a regional model there. 10 of our universities, combining both the education department and the computer science department, are working to support the teachers in their regions, running events on a pretty much a weekly basis, holding conferences, providing dedicated support to the teachers in their area. Within the network of excellence, we've designated just over 400 master teachers as the experts in computer science teaching in school. These have to be teachers. I'm not allowed to be a master teacher because I'm not working in school anymore. So the 400 plus master teachers are all teachers. They have some background in computer science, or they've done professional development to give them that background. They're also really good at passing on that knowledge to teachers in the schools near them. And so they take responsibility for 40 or so schools near them, run the hub meetings, set up, provide coffee and cake and some training after school once a term or so to pass on their knowledge of computer science and of teaching to the teachers near them. And that seems to have worked. For primary, the challenge was much bigger. So we have lots of primary schools and hardly any computer science teachers. So we got some funding from the Department for Education to create this barefoot computing program. Barefoot computing starts from the idea that you don't need a degree in computer science to be able to teach primary children computer science. You just need to know enough to be able to deliver that primary curriculum. And so we focused so much on, yes, computational thinking, but also on the rest of the curriculum of making the connections between these big ideas in computer science and what teachers are already familiar with, teaching maths, teaching first language, teaching the humanities, and trying to connect those subjects with some of the big ideas in computer science. We've produced the subject knowledge packs, so QuickStart Computing aimed directly at that subject knowledge gap. It's enough subject knowledge to be able to teach the primary curriculum, the secondary curriculum, again funded by government, so available for free for any teachers to download. And we've also created the certificate, British Computer Society's Certificate in Computer Science Teaching, which teachers can choose to take themselves. It's not, a required accreditation, but it's a very useful combination portfolio approach to professional development. So they have to do 20 or so hours of professional development, at least 10 of which has to be face-to-face. They can choose what works for them for that. They have to be able to write a computer program. Part of the certificate is show us your code. Create something that you could use in class. Seating plan software for secondary school, drill and practice game for primary school, write some code and have that reviewed by an assessor. And then the pedagogy side is carrying out a classroom investigation, doing a little bit of action research. Seems to be working very, very well. I'm very impressed by the work that's gone into that. Okay, looking now at the teaching materials, we have again, coming back to Tim Oates, a very persuasive case that getting textbooks right is really important, not just for computer science, but across the curriculum. So taking that as a starting point, we pardon me, created a set of guidelines for what a good textbook should be, or a good set of resources should be in computer science. We have a number of textbook schemes which have met those criteria. So the one I've written, a little plug here, Switched On Computing. We have Mark Dorling working on Compute It up in secondary education, and a number of other schemes that are available. I mentioned Switched On Computing because we've got the Spanish translation of that, which I'm very proud of, I must say. We also have Code Club, this after-school coding club, where they make their resources, which are, yes, used after school, but available to teachers to use in the curriculum as well. Some really nice activities in Scratch, in Python. But judging by the evaluation, don't expect it to do wonders for children's computational thinking. CAS members have shared generously the things they're using in class. They've made PowerPoint presentations, they've created educational resources, they're sharing them with the rest of the community for free under a Creative Commons license. We also have a national broadcaster, the BBC, developed or led as was the lead partner in a whole consortium that developed these tiny wee little bare circuit board machines called the BBC Microbit, £13, pretty much €13 these days, which they put into the hands of every 11-year-old a couple of years ago. So every 11-year-old in England was given one of these with the idea of go off and make something with this. And of course, that reaches some, but really what we want is doing this in school. And there's lovely block-based language like Scratch for writing code for one of those devices. And the other success story, of course, is the Raspberry Pi. Computer about so big, about 35 euros, general purpose computer. Plug in a monitor, plug in a keyboard, plug in a mouse. You've got a Linux operating system there, and you can write code on this. Not only can you write code, we can do that on any machine now, but you've got access to these general purpose input-output pins. The really interesting thing about the Raspberry Pi is, remember those A-level projects about go and make something amazing? The Raspberry Pi is very often the platform for the best of those projects. And Cambridge University saying, please, don't worry about the qualification, just go and make something interesting with the Raspberry Pi. Thank you, Jesus, that's kind, sorry. Excuse me. Turning now to those incentives and drivers, and I want to use this as an opportunity just to share with you how well this has gone to a greater or lesser extent. So Barefoot Computing, BT is now the sponsor for Barefoot, did the survey before we introduced the curriculum. So April 2014, we asked teachers, how confident are you teaching this new subject? And 33% of them said that they felt confident with the computing curriculum. 33% teaching a subject that they'd never learnt. Wasn't really that bad. We went back last August and asked teachers, August 2016, how confident are you now teaching computing? And astonishingly, 81% said they were confident teaching computing. So we feel quite proud of how well the professional development has gone, although many of us aren't entirely convinced that the 81% figure is entirely accurate. The teacher training thing remains a challenge. We have generous tax-free scholarships for those with a good degree in computer science who choose to become a secondary computer science teacher. So for your training year, there's a tax-free £27,000 scholarship for those with first-class degrees or PhDs in computer science. Bizarrely, not many people with first-class degrees or PhDs in computer science choose to become secondary computer science teachers. I don't know why that would be. We have had folks applying for this and going on to become the new master teachers, the next generation of great teachers of computing, generous funding for that. Recruiting into initial teacher training for secondary computer science remains a challenge. It's not got worse. In fact, it's got slightly better. 2012, 2013, when it was the old ICT curriculum, we had a good 250 unfilled places for initial teacher training courses. Nowadays, it's about the 200 mark, but it's still, there are empty places on teacher training courses at Roehampton and elsewhere. We've not been able to persuade folks with a background in computer science, either from their university study or from industry. Not enough of them are choosing to become computer science specialists, so more work required there. The worry is that not all secondary schools are buying into computing. Yes, it's on the national curriculum, but the actual curriculum as taught is determined by head teachers. So we've tried to make a persuasive argument to head teachers to why they should be including this on their school timetable. So we've done work around that as well. One of the incentives is this school performance measure we have in England called the English Baccalaureate, where you have to do, in order to get the baccalaureate, which is really just a school performance thing rather than a certificate for the student, you have to do 8 fairly rigorous academic subjects. We made the case that computer science was sufficiently academic, sufficiently rigorous to count as one of the sciences there. So as long as you study 3 sciences, pass 2 of them, that counts towards the baccalaureate measure. And that seems to have had some impact in terms of schools offering it. Because now we have 57% of state schools entered students for computer science. If we look at the main categories of schools, it goes as high as 70%. Because small schools such as pupil referral units, special schools, tend not to be offering computer science. So 57% of state-funded schools are offering the qualification. But within those schools, it's a very small group, typically, who actually choose to take the qualification. And we need to do some work around that. The numbers are increasing. So when we started, the red line is the computer science. So it increased quite rapidly. There are changes to the assessment method, or assessment approach. So it's slightly leveled off the most recent year, but it's going in the right direction, we think. There are big issues around gender and inclusion. So computing is way over the right-hand side of the graph. 80% of the students who took the GCSE 16 plus qualification were male. Why is that? When in primary, it's 50-50 because everybody has to do it. Lower secondary, it's 50-50. But when they get the choice come GCSE, only 20% of those who choose are female. That can't be what we shouldn't be satisfied with this. At A-level, there is still an upward trend, slightly slower than you saw with the introduction of the qualification at GCSE, but certainly heading in the right direction. But it's a very small cohort of students. We had about 7,000 students across the UK who took A-level computer science last summer. We want that to be more than that, obviously. And the gender imbalance is even worse at A-level. So we have less than 10% of A-level students were female last summer. That's less than 700 students across the female students in the UK took computer science at A-level. It's better at university than it is at A-level. Talking of university, there's this weird thing going on. If you want to study computer science at a leading English university, the recommendation is do 2 maths A-levels because maths is a proxy for clever student who works hard, it seems. They won't turn you away with an A-level in computer science, but university computer science departments are not yet requiring it. What they are saying is that A-level computer science is really useful for a whole host of other disciplines. If you want to study economics or mathematics or engineering or physics at university, then studying computer science at A-level is helpful for that. And I'd like more subjects to recognize that some qualification in computer science at A-level at school really does help, considering the role of digital technology in these domains. My data for for university is a little bit out of date. We're starting to see an upward increase in the number of students starting computer science degrees at university, and we're hopeful that that will now continue. But it's going to take a while before those who are learning to program BBOTs and Scratch in primary school are applying for university places. I'm optimistic. Our inspectorate, Ofsted, have criteria, or at least have shared criteria, yeah, I know, okay, around what good computer science looks like. And we have the Royal Society, our leading scientific academy, publishing a report on the state of computing education. I think it's 2 weeks on Friday, 3 weeks on Friday that will be coming out. So they're going to speak with authority. I've just been making this up. The key thing to leave you with is this notion of entitlement. That the interesting thing we did was not merely making computing available to children in primary school or to lower secondary school, but saying that this was a subject everybody should study. The girls and the boys, the ones from the middle class homes and the ones from the significantly less affluent backgrounds. The children from any ethnic group. Computing is a subject which all of them should be studying, we think. So if it wasn't for catching a plane, I'd go through this in a bit more detail. Just getting the framework isn't enough. It's about the delivery. It's about the implementation of that. My advice to you is plan in terms of this coherence model. Just the framework alone isn't enough. Just getting teachers able to teach this isn't enough. It's all of these things need to work together. Training the resources matter. Yeah, think about the pedagogy. This is such exciting times because we're figuring out for ourselves what works. Transition is really interesting. Do you do it all at once or do you just gradually phase it through? We did it all at once. And yeah, again, it's for everybody. It's not just for a few. It is for all. So thank you very much. As I say, great pleasure to be here. Details there. Thank you.